Swayam Prabha. Digital India. Educated India.
In the previous two lectures, we have considered two ways of finding suitable similarity transformation for solving the algebraic eigenvalue problem. In this lecture, we will briefly discuss the other two. The first that we discuss now is the method based on matrix decompositions or factorizations. The most important matrix decomposition for eigenvalue problem is the QR decomposition. In these two chapters of the book, you will find that there are quite a few sections with asterisks. These star marked sections are a little advanced, so we will not cover these topics in depth, and rather we will try to concentrate on methods so far as its use is concerned. First, the idea of QR decomposition. The decomposition itself is quite straightforward. The QR decomposition is the decomposition of a matrix into two factors, Q and R, in which the first one, the Q factor, is orthogonal, and the second one, the factor R, is upper triangular. The good point about QR decomposition is that it always exists. Whatever matrix you give, one can decompose it into Q and R factors. So, as long as you give a square matrix, the Q and R factors will be square. So, for every square matrix you have a QR decomposition, so it will always exist. Next, performing this decomposition is pretty straightforward. In fact, if you have come to this point through the exercises in the previous chapters of the textbook, then you would have already decomposed one matrix into Q and R factors. In chapter 4, one very simple QR decomposition problem was set for you as an exercise, in which the steps for the decomposition were also suggested. And the third important issue in QR decomposition is that it has a number of properties which are extremely crucial for the solution of eigenvalue problem. First, we see how we conduct the QR decomposition of a given matrix. Say this is the matrix A, in which A1, A2, etc. are columns. So, this is to be decomposed into Q and R factors. This matrix is orthogonal. That means its columns Q1, Q2, Q3 are all unit vectors which are mutually orthogonal, and this is an upper triangular matrix. Below the main diagonal, everything else is 0. Now, first we quickly review the same process of effecting this decomposition which was suggested in the exercise of chapter 4. This method is based on the procedure of Gram-Schmidt orthogonalization, and Gram-Schmidt orthogonalization process itself is actually another very simple algorithm which was introduced even earlier in the exercise of chapter 3. Now, here we again, just like our normal decomposition processes, we try to determine these decomposed parts through term by term multiplication. So, first we can write A1 as the first column of this matrix product, and that will be this matrix multiplied with the first column. Now, that will give us R11 into Q1 plus everything else is 0. So, that means we get R11 Q1 as the first column of the matrix A. Now, the matrix Q is supposed to be orthogonal. that means this vector column vector q1 should be a unit vector, and that will mean that the entire magnitude of this vector a1 should be r11. So, what we do? We take the norm on both sides and we find that the norm of a1 is r11. Once we find r11, then we can divide this vector a1 by r11, that gives us the unit vector q1. Precisely this step you will find when you try to conduct this whole thing for j equal to 1. First, this part is missing for j equal to 1 because there is only one term in the sum and there is no previous I. Okay. So, this part is missing. You start from this part. Here also this sum is completely missing and you have this aj itself, a1 itself sitting in the place of aj prime, and then r11 is its norm as I just now mentioned, and when you divide that column vector a1 with r11 you get q1. After that you equate the second columns. Second column a2 is r12 into the first column here plus r22 into the second column here, right. Other terms are 0. So, from here the actual work starts. So, r12 into q1 plus r22 into q2 is the second column. You do not know anything on this side except q1. On this side you know a2. Now, if you know q1 and you also know that q2 is supposed to be orthogonal to q1, then both sides, if you take inner product with q1, that is you multiply this both sides of the equation with q1 transpose, then here q1 transpose q2 will become 0, and here you will have q1 transpose q1 is 1, and then what will remain on this side is r12, and that is q1 transpose a2. That is what you find here. For j equal to 2, only I equal to 1 is possible, and r12 you get as q1 transpose a2. After you have found that, you can subtract that from a2, and in this particular case this summation will include a single term, this q1 transpose a2. After you remove that, that is this r12 into q1, this part r12 q1. Now that you have got r12 q1, you subtract from a2, what you are left with is this, that is demarcated here as a2 prime, and if you are left with this thing only, then its norm will give you r22, right. So, its norm will give you r22. Once you have found r22, then you can divide the remaining thing a2 minus that stuff with r22, and you get the unit vector q2, that is here. This way you keep on proceeding. So, in the next step you will find r13, r23, and then the two terms subtracted from a3 will give you r33 into q3. Its mod will give you r33, and when you divide with r33 you will get q3. The trouble will arise if you find that r33 or rkk at the kth point, if rkk turns out to be 0, then what? Then you cannot divide this. Still rkk equal to 0 is a valid output, which you will place in this location wherever in the diagonal entry it is supposed to come. That will signify that the given matrix is singular. Apart from that, so far as the question of determining qk is concerned, it is not a problem at all, because qk in the sum for ak is actually not making a contribution, because it is supposed to get multiplied with 0 to give the contribution. The trouble started because this entire vector aj prime turned out to be 0. At that stage you cannot divide it like this, and therefore you cannot get qk by this formula, but that does not mean that the process stops there. This rjj or rkk being 0 only means that Qk is left unconstrained. Qk expression is not available from here, and that means that as long as Qk satisfies, that column satisfies the orthogonality requirements, it is fine. So, what you do till now, whatever columns of matrix Q you have found, Q1, Q2, Q3 up to Qk minus 1, any new unit vector which is orthogonal to all these k minus 1 old column vectors is acceptable as Qk. So, that means that if Rjj is non-zero, then this is a constraint based on which you determine Qj. If Rjj is 0, then that constraint is removed, and in that situation any vector satisfying this orthogonality requirement is acceptable for Qj. With this process till the end, you can go and decompose the matrix into Q and R factors. Now, this is a very simple straightforward method by which you can effect the QR decomposition. However, I should mention for record that the sophisticated or practical methods which are utilized in most of the computational algorithms is actually not this. Though this is a valid method, but actually the QR decomposition is effected in most professional programs is through householder transformations. The same householder transformation which we studied in the previous lecture, but with a little difference. Here there are two small differences compared to the way we applied householder transformation in the previous lecture. In the previous lecture, we were using householder transformation matrix on both sides, left as well as right, because we were concerned with similarity transformations. Right now, we are concerned with actually factoring a given matrix into two factors Q and R. We are not yet so much concerned with a similarity transformation. We will be talking about similarity transformation based on this a little later, but right now our focus is on effecting a QR decomposition, and therefore, there is no compulsion for us to multiply on both sides to maintain the similarity. Our main focus is to effect a QR decomposition. This is one point. Second point we arrive at when we consider this situation, that we apply a householder transformation on a given matrix in which we do not consider this much as U, but we consider this whole thing as U. If we consider this whole thing as U and work out the corresponding V as we did in the previous lecture, then what will happen is that V will have its first entry same as the norm of this entire vector from top to bottom, and all other entries below that will be 0. Okay. That will mean that contrary to the case of the previous lecture, where this much of the first column was converted to 0, was annihilated, now this much will be annihilated in the first step. That is why here I am saying not U1, but U0. So, U0 is the entire first column. V0 is a matrix of the same dimension, a vector of the same dimension, with only the first entry being non-zero and having a magnitude same as the norm of U0. And based on that, we work out W0 and then Hn and therefore P0 in this manner. And when we apply that only on the left side, not on the right side, then from here to here all of these become 0. And next we will apply P1 based on Hn minus 1 to be operating on this much to get everything below A22 to be 0 and so on. Note that the same thing we could not do in the previous case when we were trying to effect similarity transformation, because the way the left side multiplication with the householder transformation matrix affects these entries and these entries if over the full thing. So, the similarity transformation in the previous case would require us to multiply the householder transformation matrix on this side also. That would spoil the zeros set in the left side multiplication, and that is why in the case when we were using householder transformation for tridiagonalization, then we did not want the already established zeros to be spoilt by post multiplication. That is why there we left one extra term free and applied householder transformation with one dimension less. But here we are not going to multiply the same matrix from this side, we are applying the householder transformation only one sided. So, we can take the full vector, and therefore, under the diagonal all terms we can make 0. So, with one step we with the u0 and therefore, with p0 we get the subdiagonal entries in the first column 0, and then we get this. The entire magnitude of A1, the first column, sits here, below that everything else is 0, and then P1 is applied, which will make A3 to A4 to A5 to etc. up to AN2 all 0, and so on. That will look like this. Here there will be some non-zero items, and so on. So, then we apply P2 to get everything under A33 R33 as 0, and so on. So, like that, by the time we come up to Pn minus 2, then we have got a completely upper triangular matrix. Now, note that all these transformations from P0 up to Pn minus 2 are orthogonal matrices, and therefore, this entire product Pn minus 2 to P0 is orthogonal. Product of orthogonal matrices is also an orthogonal matrix. And now, if we call Q as the transpose of this whole thing, which is this, then whatever we have pre-multiplied can be called Q transpose. So, what we have got? We have got Q transpose A as R, upper triangular matrix, which means A is equal to QR, and Q we have got stored by cumulative multiplication of the intermediate householder transformation matrices. So, this is one practical method of effecting a QR decomposition. There is one more based on the Givens rotations through one sided plane rotations. Now, before going into the application of QR decomposition in eigenvalue problems, let us quickly have a quick look at a side issue. If we already have the Q and R factors of a matrix, then even in the solution of a linear system of equations Ax equal to b, it can be utilized, because in place of A, if we write QR with Q and R factors already available in our hand, then first step is pre-multiplication with Q transpose. That will mean Rx equal to Q transpose B, and transposing a matrix and multiplying that to a vector is a task of very little computational effort. After that, what remains is Rx equal to a known vector, R being an upper triangular matrix. That means only a sequence of back substitutions will give us the solution. The solution is actually extremely cheap if we already have Q and R factors in hand, but otherwise, in order to solve this problem Ax equal to b, typically we would not go into the process of QR decomposition method, because other methods that we have studied earlier in the course are comparatively better. The actual use of QR decomposition algorithm is in solution of eigenvalue problem. Let us study the decomposition in that light. First point is that if we multiply the Q and R factors in reverse, this is a very weird proposition to begin with. We have decomposed a matrix into QR factors, and the Q and R appear Q first, R next, and now we are suggesting that let us see what we get if we multiply them in reverse, RQ. It is a weird proposition to begin with, but if we do that, then we notice something interesting. Just now we have seen that R is Q transpose A, because A is Q R. So, R is Q transpose A. So, if in place of R we write Q transpose A, then see what we have got, Q transpose A Q. Wow, what we have got is a similarity transformation. That means that if we factor a given matrix A into Q and R factors and then multiply them in reverse, then what would happen is that we would have a matrix, new matrix A prime, which is the result of a similarity transformation over A itself, the similarity transformation matrix being this same Q. Okay. So, this is a similarity transformation. Not only that, it is an orthogonal similarity transformation, because Q is orthogonal with a few interesting properties. First is that if A is symmetric, then A prime is also symmetric. That we can see because we have multiplied from both sides Q and Q transpose. So, that preserves the symmetry. Second is, if A is in upper Hessenberg form, then A prime is also in upper Hessenberg form. That you can see very easily, because in the factorization of A into Q and R factors, Q1, the first column of Q1 must be in the direction of A1. Now, if the original matrix A is in upper Hessenberg form, which is this, that means if the first column of the matrix A has only the top two terms, then first column of Q also will have only top two terms, below that everything else is 0. Next, the second column of A has 3 terms, right, but then that is the linear combination, that is a linear combination of the first two columns of Q. Now, first two columns of Q through a linear combination is giving us the second column of A, and the first column is only having 2 top terms. So, the second column can have only 3 top terms which are non-zero, okay, and so on. So, that way, proceeding that way, we find that Q also will have the same shape as A if A is Hessenberg. So, if A is Hessenberg, then Q is also Hessenberg. Now, in the reverse multiplication, what is happening is that we are multiplying RQ, right, RQ. It is this. So, that means this matrix, the first column of this matrix having only top 2 entries will mean that the first column of the product will have only top 2 entries, because the this matrix multiplied with the first column gives us the first column of the product. So, this number into first column plus this number into second column, and first column has only 1 entry and second column has only 2 entries at the top which are non-zero. So, the composition will have only 2 top entries as non-zero. Next, the second column of the product will be these 3 things into these 3 columns, and these 3 columns have up to only third entry. So, the second column will have only top 3 entries which are non-zero, and so on. So, that way you will find that if the original matrix is Hessenberg, then so is Q and so is RQ. So, that means if A is in upper Hessenberg form, then so is A prime. And now, symmetry preservation and upper Hessenberg form preservation together will mean that if the original matrix is symmetric tridiagonal, then the new matrix is also symmetric tridiagonal. So, till now we have found through these properties that through this transformation, that is factoring QR and then multiplying in the reverse order RQ, nothing is going wrong. That is, if we have given a matrix to begin with, we have got a similarity transformed form of it. If we have given a symmetric matrix, then we get back another symmetric matrix. If we have given an upper Hessenberg matrix, we get back an upper Hessenberg matrix. If we have given a symmetric tridiagonal matrix, then what we get back is also a symmetric tridiagonal matrix. That means, in the form and feature of the matrix, nothing is spoiled, nothing is lost, but the question is what is gained. And in that we find that there is a deep result which shows, which establishes that if we follow this algorithm, in one iteration not much will take place, in one step like this not much will take place, but the advantage accrues when we follow this repeatedly. What is the algorithm? Algorithm is very simple. Set A1 is equal to A, and then for k equal to 1, 2, 3, 4, 5, 6, go on doing these two steps. Decompose AK into QK RK factors, and then multiply in reverse, call it AK plus 1, RK QK. So, algorithm is just two-step algorithm. Factorize, multiply in reverse. What you get? Factorize that, multiply that in reverse, and so on. So, from A1 through these two steps you get A2. Again from that through these two steps you get A3, and so on. You go on doing this, and the deep result assures you that as k tends to infinity, that is, as you go on doing this step again and again and again, and till you reach a convergence situation where the matrix AK approaches a quasi upper triangular form, not really upper triangular, but quasi upper triangular form, and this happens for any kind of matrix. Now, what is this quasi upper triangular form? It is this form. Quasi means almost. So, in this quasi upper triangular form, it is almost upper triangular, except for some diagonal block that might remain, which is spoiling the diagonal feature, diagonal form a little, because some of its elements may be below the diagonal, and sometimes this kind of 2 by 2 diagonal blocks may come. Okay. And in this quasi upper triangular form, there is another interesting feature, that the largest magnitude eigenvalue gets organized here, next here, and so on. So, the magnitudes of the eigenvalues that you get here along the diagonal are in decreasing order. So, whenever there is a convergence to upper triangular form, you know that eigenvalues will appear in the diagonal entries, but eigenvalues get sorted also. Okay. Now, such diagonal blocks actually correspond to eigenspaces of eigenvalues which have almost equal or very close magnitudes. The decoupling, the dissociation of subspaces that is actually behind this arrangement does not work so efficiently in the case of eigenvalues which have extremely close magnitudes. Okay. That is why sometimes such diagonal blocks may appear. 2 by 2 diagonal blocks can appear when there are complex eigenvalues, complex pair of eigenvalues, and that will happen only for non-symmetric matrices, obviously. So, for such cases, this kind of blocks may remain which do not break further, because for breaking further, complex arithmetic needs to come into play to get complex values here. As long as we operate with real arithmetic, this kind of 2 by 2 blocks will remain for non-symmetric matrices if there are complex pair of eigenvalues. In particular, for symmetric matrices, a quasi upper triangular form actually will mean a quasi diagonal form, because for a symmetric matrix we have seen that symmetry is preserved. So, all these zeros will also mean that here also we have got corresponding zeros. So, we will get actually quasi diagonal form for a symmetric matrix, and such things are anyway not possible for symmetric matrices. So, this is the form to which the QR iterations will make the process converge. And finally, after we have got this kind of a form, eigenvalues are mostly available with us, except for this kind of situations where we may need to conduct a little further post processing. Now, I have told you what happens, but how this happens, this I have not told you. In my teaching, typically in mathematics teaching particularly, I try to establish most of the results, but this particular result I will not try to establish in the class. Rather, I will tell you what actually happens behind, because this is very time consuming, and it is important that when you get ready for appreciating the actual process that is happening behind, you should actually conduct the analysis on your own, possibly guided with the book. So, if you are ready for going deep into it, then I will suggest that you go through the section in the book and try to work out the whole thing on your own. Then you will get better convinced. In a nutshell, what actually happens in the background in QR method, in QR decomposition method, is that it operates on the basis of relative magnitudes of different eigenvalues, almost the way the power method used to work. But here the crude operation of power method is actually conducted in a much more sophisticated manner and at a global level. At every level, the same refinement of subspaces based on the magnitudes of their eigenvalues and the segregation of eigenspaces of small eigenvalues from the large ones takes place at all levels. Okay. So, as iterations proceed, this separation takes place over the entire spectrum of eigenvalues, and that is how the eigenvalues get sorted. Eigenvectors get arranged in suitable subspaces. The way power method works on a single vector, here the QR decomposition method at the same time operates over a multitude of eigenspaces, and inside each eigenspace it works for finer adjustments, finer sorting, and so on. All these processes take place together, and this is the reason why the diagonal blocks, it cannot break down completely if quite a few eigenvalues are of almost equal magnitude. That is the only limitation. So, if you follow through this conceptual basis, then you will find that towards the end you get subspaces which are sort of separated from each other based on their eigenvalue magnitudes. There is another important thing in relation to it, is that the rate of convergence depends, rate of segregation of different eigenspaces is actually directly related to the ratio of eigenvalues lambda I by lambda j, and this observation you can make if you go through one actual process of QR decomposition. For that, what you can do is that you can take a square matrix and write a small procedure to effect the QR decomposition, perhaps based on the method that we discussed earlier, and then actually apply this algorithm, and at the end of every iteration you see the result, intermediate results. Then you will see how the subspaces are getting separated. Based on this observation of convergence rate, there are also some sophisticated algorithms which try to shift the matrix, shifting all its eigenvalues leftward and rightward, in order to artificially decrease this lambda I minus lambda j, which will mean that if this is very small, then over successive iterations the errors will drop at very fast rate. So, such an algorithm is called QR algorithm with shift. It is a little complicated, and that is why we will not be discussing it here, but that is what is professionally implemented in most of the professional software library routines. But we will not go into this. What we will do rather is that, just like this brief introduction of the QR decomposition method for general matrices in general and for symmetric tridiagonal matrices particularly, we will consider the last topic also, the fourth method of effecting suitable similarity transformations. Now, one point that needs a special mention is that QR decomposition algorithm will operate on any matrix and try to give this kind of a quasi upper triangular form. It operates on all matrices, it is effective, but is it efficient? When we ask that question, we need to notice that implemented properly, the keyword decomposition algorithm, the iterative algorithm, is a linear time algorithm for a symmetric tri-diagonal matrix, a quadratic time algorithm for an upper Hessenberg matrix, and cubic algorithm for the general matrix. This is why we say that if you have got a symmetric matrix, then it is very important that you first reduce it to tri-diagonal form and then apply keyword decomposition, if you want to apply, even though on the full matrix also keyword decomposition method would work. Similarly, in the case of a non-symmetric matrix, it is better to reduce it first to upper Hessenberg form and then apply keyword decomposition. This is the issue which we will be considering next. The eigenvalue problem of general matrices, that is non-symmetric matrices, is relatively much more complicated, and therefore we find that the theory is much more involved and computational algorithms are A, limited, and B, relatively unstable compared to the orthogonal transformation based methods for symmetric matrices. Therefore, in this course we will not go deep into those theories, rather on these star marked sections we will very briefly gloss over and try to discuss the basic points here and the important post processing issues here. First point regarding non-symmetric matrices is that it may not be diagonalizable, a fact that we have discussed earlier. A symmetric matrix is always diagonalizable, but not so for a non-symmetric matrix. So, therefore, rather than trying to diagonalize the given matrix if it is non-symmetric, what we try here is first to triangularize it and get an upper triangular form. Next point is that with real arithmetic we cannot avoid 2 by 2 diagonal blocks. That means, even if the matrix is actually triangularizable, and that also with unitary transformations, if we stick to real arithmetic and do not go to complex arithmetic, then even triangularization process will not be really complete, because 2 by 2 diagonal blocks will remain, which will signify complex pair of eigenvalues. So, whenever complex pair of eigenvalues are there, such blocks are inevitable. Next is that the computational complexity of the algorithm is higher, convergence is slow, and sometimes the numerical process may turn out to be unstable. These are the typical difficulties with non-symmetric matrices. And what we say is a non-symmetric matrix is usually unbalanced. You see, if the norm of kth row and kth column of a matrix is same for every k, then you call that matrix as balanced. A symmetric matrix to begin with is balanced, and through orthogonal transformations it remains balanced. A non-symmetric matrix is usually unbalanced, and therefore it is prone to numerical round of errors more than the symmetric matrix algorithm. Therefore, in the case of non-symmetric matrices, as a pre-processing step, we sometimes use balancing. We try to balance the given matrix a little, and one way to balance it is that if a row is of much higher norm than the corresponding column, then we can try to adjust that by multiplication of the row with some number and division of the corresponding column with the same number, so that we can balance their norms a little bit. Now, only multiplication to a row is not correct, is not the right step to do, because that will be a transformation which will not be a similarity transformation. If we multiply a particular row with half and the corresponding column with 2, then that will be a similarity transformation, because the multiplication of the kth row with half is equivalent to a pre-multiplication with an elementary matrix, the corresponding inverse as post multiplication matrix involves the multiplication of the corresponding column with 2, and so on. So, balancing is a pre-processing step for non-symmetric matrices. Now, through the similarity transformations which are orthogonal, a balanced matrix does not go unbalanced, but if the similarity transformations that we apply, if they are not orthogonal, then even an originally balanced matrix may go unbalanced again. Now, what we do with the matrix in order to triangularize it? So, there are three possible alternatives for the first step for a non-symmetric matrix. The first step for a non-symmetric matrix is to reduce it to upper Hessenberg form, which you can do with a fixed number of arithmetic operations without any iterative process, and then further we will conduct iterations on that upper Hessenberg matrix. So, the reduction to Hessenberg form can be done in several different ways. One is a full sweep of Gibbons rotation, as we have discussed earlier. Another is a sequence of n minus 2 steps of Householder transformations, which also we have discussed in the previous lecture. Now, these two things, one of the two, each of them converts a symmetric matrix into symmetric tridiagonal form. The same operations in the case of a non-symmetric matrix will convert it to the upper Hessenberg form. The zeros under the subdiagonal will be arrived at, but that will not mean that over the super diagonal also you will get 0, that you will not get in general. Apart from these two, for a non-symmetric matrix you can also apply a third method, which is a cycle of coordinated Gaussian elimination. To make the record straight, this kind of a thing is possible for a symmetric matrix also, but in the case of a symmetric matrix, this we will typically not do, because in the symmetric matrix case the orthogonal transformation based algorithms are superior. Here there is no symmetry to preserve, and therefore it really does not harm to take the third option. In the third option, what we do? We apply Gaussian elimination in a well coordinated orchestrated manner. Note that the straightforward Gaussian elimination which we were applying earlier for solving a linear system of equations, that was only based on rows, only row operations we were doing. That same thing we cannot do as it is here, because every step, every transformation of the matrix has to be made through a similarity transformation. That means whatever matrix we pre-multiply with, we need to post-multiply with the corresponding inverse, and therefore the Gaussian elimination here must be coordinated. So, this Gaussian elimination or elementary transformations which are applied in a coordinated manner are actually applied from two sides, one through a pre-multiplication and the other through a post-multiplication. That means the pre-multiplying matrix corresponding to the elementary row transformation and the post-multiplying matrix corresponding to the matching column transformation must be inverses of each other. Okay. That is how the similarity will be maintained. So, there are two kinds of steps in these elementary transformations, as always. One is the pivoting and the other is the elimination. So, in the pivoting step, typically you try to interchange rows and accordingly interchange columns also. And in the elimination step, typical pre-multiplying factor will look like this, which will mean subtraction of some multiple of the pivotal row from the lower rows, that is why minus k here, this is a vector, and the corresponding column transformation here, which will be equivalent to appropriate addition of all the later rows, all the right side rows to that pivot, right side columns, columns into the pivotal column. This will actually compose the elimination step. Through such pivotal, through such pivoting and elimination steps, we convert it into the Hessenberg form first, and then we apply the QR algorithm on the Hessenberg matrix. And in that process, as we keep on applying the QR iterations, as soon as a subdiagonal 0 appears, we split the matrix into 2 parts and continue with the smaller parts, and so on. And if towards the end a smaller part turns out to be a 1 by 1 part, then that itself is an eigenvalue. If the smaller part turns out to be a 2 by 2 submatrix, then from that, through a quadratic equation solving, we determine 2 eigenvalues, and so on. So like that, we keep on decomposing into smaller diagonal blocks and solve the eigenvalue problem in terms of only eigenvalues to begin with. After that is over, then we go into a method which is called inverse iteration. This is a very valuable method, because at the end of the reduction up to upper triangular form, all that you have is only eigenvalues and not eigenvectors. And quite often it may also happen that the eigenvalues are also only crude estimates. In such a situation, when you have got an estimate of the eigenvalues, not their exact values, then to refine the values of the eigenvalues and the corresponding eigenvectors, to get the values of the eigenvectors, inverse iteration comes as a very good method. For that, the assumption is that matrix A has a complete set of eigenvectors, and lambda I 0 is a good estimate of the ith eigenvalue of A, lambda I. Okay. So, lambda I 0 is an estimate of lambda I. In that case, what you do is that in order to find the eigenvalue lambda I precisely and to determine the corresponding eigenvector, you first make a guess of any random vector y 0 with magnitude 1 and solve this system. As you solve this system, you find that the solution y is a very good estimate of the eigenvector V I. This is very interesting. The reason is that if we are constructing this matrix A minus lambda I 0 I, that will mean that all eigenvalues of this matrix get shifted by lambda I 0. If lambda I 0 were an exact estimate of lambda I, then this would be a singular matrix, and in that case, as it is, you would not be able to solve it. But if it is a good estimate, but estimate nevertheless, not exact value, then that will mean that through this shifting, the ith lambda, ith eigenvalue becomes of very small magnitude, and that means in the solution, which is basically y, that is this matrix inverse into y 0, you get that particular eigenvector overemphasized, okay, because the eigenvalue which is extremely small in the inverse, the corresponding eigenvalue will be extremely large. Okay. So, that eigenvector gets overemphasized, and then therefore, in y you will find that the components of the other eigenvectors become very less in comparison to the eigenvector corresponding to which we have made an estimate here. Okay. And y is a good estimate of the corresponding eigenvector, and through a little further processing, you can see that the difference of the correct value and estimate will be given by this. So, that therefore, the expression here gives you an improvement in the estimate of the eigenvalue, and then that estimate you can utilize here and continue this inverse iteration. Now, this is a very peculiar algorithm in the sense that here you cannot complain of ill conditioning in the solution process of this linear system, because it is that ill conditioning itself that is actually driving this algorithm. That is, because of that ill conditioning, your intended eigenvector is actually getting expressed, is getting emphasized in the solution process, and you are able to identify it. Not only that, in the later iterations towards the convergence, this matrix will become even more and more ill conditioned, because lambda I estimates will become more and more precise. So, this algorithm is tricky, and we have to handle it carefully. The algorithm is start with an estimated eigenvalue and guess y0, which is normalized with magnitude 1, and then every iteration you solve the system, find and normalize the next y0 in place of y0, then it will be y1, y2, y3 and so on, next vectors to be used here in this system. So, normalize this and make the improvement over the eigenvalue, and then if the previous right side and the new right side are extremely close to each other, then terminate. That is the convergence. So, this is the algorithm which gives you refinement over the eigenvalues and the values of the corresponding eigenvectors. So, this can be done as a post processing step after you have triangularized the matrix. This can work for symmetric as well as non-symmetric matrices. Now, the important issues here is that every time that you update the eigenvalue, the coefficient matrix actually changes. That may mean the solution of this system may turn out to be more and more costly. So, one way to handle this is to update the eigenvalues only once in a while, not at every iteration. Next, a small artificial number may need to be used as an artificial pivot while solving this linear system, because as we were discussing earlier, this matrix is known to be ill conditioned. Okay. So, therefore, when you try to pivot in the linear system solution, you will have difficulty in pivoting, because all the entries, all the candidates for pivoting will turn out to be extremely small, and therefore, a tiny number of your choice you can insert there as an artificial pivot rather than the 0 that might appear otherwise. The point is that in the beginning we said that this works under the assumption that the matrix has a full set of n eigenvectors. If the matrix is defective or if it has complex eigenvalues, in that case it may not converge as easily as you would expect, because the underlying theory expects the expression of the chosen vector in the form of a sum of a linear combination of eigenvectors, and that may not happen, that may not be possible in case of a defective matrix. And then in case of complex eigenvalues, the pair of complex eigenvalues are both of the same magnitude, and therefore, for that eigenvalue the situation may be tricky, because the magnitude, only one magnitude does not get expressed equally high, unequally high compared to others, because two eigenvalues are of the same magnitude at least. Even repeated eigenvalues or extremely close magnitude eigenvalues will similarly inhibit the process. Now, with this much we complete our discussion on the eigenvalue method, and at the end we need to have a quick look at the entire spectrum of methods that we have studied till now in the last 5 lectures, and make a sort of choice on the kind of methods that we typically utilize while solving eigenvalue problems of different kinds of matrices, kinds and sizes. There are 3 parts, 3 columns here. One is reduction, kind of pre-processing, then the actual main algorithm, and then the post processing. For general matrices, if the size is extremely small, up to 4, then you do not need any sophisticated method. You can reduce it based on definition itself, get the characteristic polynomial, and the algorithm is actually simply polynomial root finding, and after that you solve the linear systems to get the eigenvectors. For intermediate size matrices, say 4 to 12, you can either use Jacobi sweeps to reduce the matrix to an extent, and then rather than using further sweeps, you can use selective Jacobi rotations to diagonalize it completely, no post processing required. Alternatively, for this range of size of the matrix symmetric, you can first try diagonalize by Given's rotation or Householder methods, and then you can use Sturm sequence property, and bracket and bisection, use bracketing and bisection to find the rough eigenvalues. Once the rough eigenvalues are determined, then you can use inverse iteration to refine the eigenvalues and determine the eigenvectors. If you have symmetric matrices which are large, say larger than 12 by 12 size, then reduction must be carried on for the sake of efficiency up to tridiagonalization. Here usually you will use Householder method, because that is much more efficient compared to Gibbons rotation for larger matrices. And then the main algorithm will be typically QR decomposition iterations for symmetric tridiagonal matrices. If you are working with non-symmetric matrix with intermediate or large size, then first you will reduce it through balancing and then to the Hessenberg form, either these methods or through Gaussian elimination based methods, and then you can use QR decomposition iterations to triangularize the matrix and get the eigenvalues, and finally you can use inverse iteration to refine the eigenvalues and determine the eigenvectors. For general matrices, symmetric as well as non-symmetric, if the matrix is very, very large, but the requirement is only selective, that is, if you want to determine only the top and bottom eigenvalues, or you want to determine top few eigenvalues, in such situations you can use power method, shift and deflation to pick up only those pieces of information which you need. So, with this we complete this small submodule of the algebraic eigenvalue problem. Earlier we studied the first submodule of linear algebra, that was systems of linear equations. Now, in the next lecture we will combine these two and see the connections between these two problems into the one of the most important lessons of this course, which is singular value decomposition, that we will discuss in the next lecture. Thank you.